Hello, welcome to Talk Math. Today we're going to be doing the integration of equalifier round from the November 2020 HMMT. Now, I did take this test live, so I've seen these problems before, and I was able to get 15 out of the 20. And the way this test works is you have 30 minutes to complete the following 20 problems, but problem number 20 is an estimation problem, so that they could break ties. So in this video, I'm going to be going through problem by problem, and not trying to go as fast as I can to do it in the 30-minute time limit. I'm going to be thoroughly explaining how to do each problem instead. So starting off with question number 1, as we have the integral from 20 to 2020 of absolute value of x minus 20 plus the absolute value of x minus 2020 dx. Now, I realize that on this interval from 20 to 2020, this is always going to be positive. So we really should have the integral from 20 to 2020 of x minus 20. And then right here, this part's always going to be negative. So then we have minus x plus 2020 dx. Now the x's will cancel, leaving us with the integral from 20 to 2020 of 2000 dx, which leaves us with 2,000 times 2,000, which equals 4 and 6 zeros. And that is the answer. Okay. Moving on to question number 2. I immediately think of u substitution because we want this x to go in front, so we're going to do u equals 1 minus x squared. So when we do that, u equals 1 minus x squared. So then du is going to be equal to negative 2x dx. So now we have that x dx equals negative du over 2. So now we're going to have the integral. So now plugging in 0 to x, we have starting from 1. And then plugging in 1, we are going to go to 0 of, now we have the root u. And then the x dx is equal to negative du over 2. I'm going to use the negative sign to flip the bounds. So this equals the integral from 0 to 1 of root u over 2 du. So now this becomes pretty simple. So this is u to the 1/2 power. So it's going to be 2/3 times u to the 3/2 over 2. Now we can check to make sure that works. So we take the derivative, that cancels out, leaving us the u to 1/2 over 2. Now evaluate that from 0 to 1. Plugging in 1, that just leaves us with 1/3 minus 0. Moving on to question number 3. I immediately see that we have a whole bunch of e to the x's that are nested. And so I'm going to expand that out because we can use the chain rule. So we have the integral of e to the x times e to the x times e to the x dx. Now, I realize that if we were to just take the derivative of this term right here, by the chain rule, then we end up having to multiply by this, and then again, we have to multiply by this. So this is just the derivative of e to the e to the e to the x plus c. Because when we do that, the chain rule will give us all these terms being multiplied. Now, moving on to question 4. This is interesting because we have maximums and minimums. So when I see this, I'm actually going to break up this question into multiple intervals. One from the interval from 0 to 5, one from 5 to 15, and one from 15 to 20. So let's integral from 0 to 5 of, now the minimum between 15 and x on this interval will always be x, because x is between 0 and 5. So we'll have the maximum of 5 comma x dx, plus now in the next interval, we'll have from 5 to 15. Now from 5 to 15, the minimum, again, will always be x. So we'll have the maximum of 5 comma x dx, and then plus on the interval from 15 to 20, well, the minimum will always be 15 dx. Now for this first part, the maximum of 5 and x will always be 5 on this interval. So we have the integral from 0 to 5 of 5, which just leaves us with 25, plus now in this interval, the maximum of 5 and x will be x. So we have plus 1/2 x squared, taking the integral from 5 to 15. And then finally, we have plus 5 times 15 for the last integral. So now what we need to do is find what this equals. So plugging in 15 squared is 225. So you have 225 over 2 minus 25 over 2. And then plus 25 plus 75 is plus 100. So that gives us 100 plus 100, which equals 200. Sorry, I ended up running off the page on my last recording, so I restarted this problem and moved it on a separate piece of paper. So moving on to problem number 5, we have the integral of log cubed of x dx. Now, I'm immediately going to do u equals log x because I want to get rid of the log x, because that's pretty ugly. So u equals log of x, so then e to the u equals x. So then e to the u du equals dx. Okay, so now plugging this in, we have the integral of log of x is now u cubed, and then dx is e to the u du. Now this becomes a simple integration by parts or tabular. So we're going to differentiate u cubed and integrate e to the u. So integrating e to the u multiple times, it just leaves us with an e to the u. Differentiating u cubed, we'll have 3u squared, and then 6u, and then 6. So going diagonally, we have u cubed e to the u minus 3u squared e to the u plus 6u e to the u minus 6 e to the u. Now what we need to do is plug back in the u equals log x, But before I do that, I'm going to note I could factor out a e to the u from all of these terms. And when I do that, I can plug in log x, then that log x will cancel, just give me us an x. So I'm going to factor out that x to the very front. Now we're going to have a log cubed of x minus 3 log squared of x plus 6 log x minus 6. And then don't forget the plus c as always, and we're done with this problem. Okay, now moving on to question number 6, we have this weird expression. We have sine of x to the e to the x with an e to the x and some trig functions coming later. Now when I see this, I immediately want to differentiate this first term right here, because I know whenever you have a function to some other function's power, the derivative will look something like that itself times some other jumble terms that look something along those lines. So let's try that. So let's see what happens when we take the derivative of sine of x to the power e to the x. While doing that, if we set this equal to y, then we have the natural log of y equals natural log of sine of x times e to the x. Okay, now taking the derivative of both sides, we have y prime over y implicitly equals the derivative of e to the x is e to the x times ln of sine of x. Now, taking the derivative of this times e to the x, we'll have cosine of x over sine of x. Now I'm going to multiply both sides by y, so we have y prime equals, and remember, y is equal to this, so we have sine of x to the power e to the x times this part right here. And now I'm going to factor out an e to the x also, so bring that to the front. And then we have a natural log of sine of x, and then we have a plus cotangent of x. Now let's compare what we have. Well, if we look, we have the sine to the e to the x, another e to the x, and then the same exact term, which I wrote in reverse. So this is the exact same thing, so this is actually the integral of this function. So that's a very key thing to look out for, is to note that anything of this form will give you something looking similar to that. So we have our answer is sine of x to the power e to the x plus c as always, and we're done with the problem. Okay, moving on to question number 7, we have a whole bunch of nested fractions. And so let's simplify that out first to see where that gets us. So we have the integral from 0 to 1 of 1 over 1 plus, and now we have a 1 over, now this 1 plus 1 over x will become a 2 plus x over 1 plus x dx. Now this equals the integral from 0 to 1 of 1 over 1 plus x over 2 plus x dx. And now that equals, going all the way back, we're adding a 2 plus x to the numerator will give us a 3 plus 2x, but that will be on the denominator. So you have 3 plus 2x over, and then this will come to the numerator, giving us a 2 plus x dx. So now we've combined all those fractions, and it's a much easier form to work with. So in order to proceed from here, I'm actually going to double it and multiply it by 1/2, because I want these two x's to go away, and you'll see what I mean by that in a second. So doubling it and 1/2ing it, we have 1/2 times the integral from 0 to 1, and now doubling the numerator, we have a 2x plus 4 over 2x plus 3 dx. And now the reason I wanted to do this is because we can separate this into a 2x plus 3 and a 1. And when we do that, we have the integral from 0 to 1 of 2x plus 3 over 2x plus 3 plus 1 over 2x plus 3 dx. Now this first part will cancel, giving us a 1, and the second part we can integrate using natural log. So integrating, we have a 1/2 times, integrating 1 we get x, plus 1/2 natural log of the absolute value of 2x plus 3, and that's our integral. So now what we need to do is evaluate that from 0 to 1. So plugging in 1, we get 1/2 times 1 plus 1/2 natural log of 5, and then we have a minus 1/2, plugging in 0 will give us a 1/2 natural log 3. Okay, so now what we need to do is simplify, so we have 1/2 plus 1/4 ln 5 minus 1/4 ln 3. So I'm going to combine these natural logs and rewrite this finally as 1/2 plus 1/4 ln of 5/3, and that's going to be my final form of the answer, although there are many acceptable forms. Okay, moving on to question number 8, we see we have another weird-looking expression, e to the 1 over log x over x times log squared of x. And now again, similar to question 6, I want to think, what happens if we were to take the derivative of e to the power 1 over log x? Because by chain rule, we'd have to take the derivative of this exponent, and that should give us something similar to what we see on the denominator. So let's try that out and see what happens if we get e to the 1 over log of x. Now taking the derivative of this, we're going to have an e to the 1 over log x. And then chain rule, take the derivative of this, we're going to have a negative 1 over log squared of x. And then we have taking the derivative of log x, we'll have a 1 over x. So now I'm going to rewrite this whole expression, which is going to be e to the 1 over log of x, and then negative x log squared of x. Now how similar is this? Well, it's the same exact thing, except for the negative sign. So all we need to do is just multiply our original expression by a negative sign, and we're actually done with the problem. So it becomes negative e to the power 1 over log of x plus c, and we're done with the problem. So it's actually pretty simple once we just realize that all we need to do is look at something smaller inside the integral. Now, moving on to question number 9, we have a whole bunch of trig. Now, my immediate thought is that maybe we can try simplifying the sine of x plus cosine x using double angle formula for sine, but that actually won't get us anywhere because there's no really easy way to simplify the denominator, sine to the fourth plus cosine to the fourth. So my second thought is to divide by cosine to the fourth of x, and the reason why is because that will change this from being sine and cosines into tangents and secants. And that could be helpful because the derivative of tangent is secant squared. So let's see where that gets us. So you have the integral from 0 to pi over 2 of dividing by cosine to the fourth. On the numerator, it will leave us with a sine of x over cosine cubed. And then on the denominator, we'll have a tangent to the fourth plus 1 dx. Now again, I want this in terms of secants and tangents, so I'm going to take one of these sines over cosines and rewrite that as a tangent. So you have the integral from 0 to pi over 2 of tangent x, and now I'm going to take the other 1 over cosine squared and make that into a secant squared of x. Now we have all over 1 plus tangent to the fourth of x. And now this form looks much better, and the reason why is because we have the secant squared is the derivative of tangent. So maybe we want to do a u sub u equals tangent of x. Looking into what that would do, we'd have a 1 plus u to the fourth, u over 1 plus u to the fourth. And that also isn't that easy to integrate. However, we see that if we were to actually do u equals tangent squared, it might become simpler. So if we do u equals tangent squared of x, then taking the derivative, we would get du equals 2 tangent x secant squared of x. And that is what appears on the numerator with this 2 in front. So let's try that instead. Dx. So plugging that in, we have the integral from plugging in 0 into this, we have from 0, and plugging in tangent of pi over 2 is infinity. Now we're going to have on the numerator, just a 1/2 over, and on the denominator, a 1 plus u squared du. Now this is much easier to integrate because it's just your arctangent. So you have 1/2 arctangent of u evaluated from 0 to infinity. So arctangent of infinity is going to be pi over 2, and then arctangent of 0 is 0, so that doesn't matter, and we are left with pi over 4 as our final answer. Okay, moving on to question 10. Again, we have another really messy form. I see we have a 1 minus x squared and a 1 plus inverse sine of x all in the denominator in a square root. And now, again, when I see this, it's very similar to question 8 and question 6, because I see this 1 over root 1 minus x squared in the front, and that happens to be the derivative of inverse sine of x. So maybe that appears by some form of chain rule. So now what else do we have? We have this 1 plus sine x that's in the denominator under a square root. Well, how would that get there in the first place? It would get there if it were taking the derivative of the square root of that, because then by power rule, it would become a negative 1/2. So let's see what would happen if we were to take the derivative of 1 root 1 plus inverse sine of x. Because looking through it, this would become on the denominator, still under the square root, and we'd also, by chain rule, get something similar to the front. So taking the derivative, we're going to be left with 1/2 times 1 over root 1 plus arc sine x. And then by chain rule, we're going to have a times 1 over root 1 minus x squared. Now this is actually, looking back, it is the same thing, except for the 1/2 in front. So all we need to do is double our initial expression, 2 times root 1 plus arc sine of x, and then add c, and we're done with the problem. So a lot of these are actually very easy if you note that their derivatives of some function appear somewhere else in the problem. So moving on to question 11, my immediate thought is to maybe try integrating with respect to one variable and then the other, and because it doesn't look too bad to integrate with respect to the first variable. However, if you actually try that, you'll see that it doesn't become easy to integrate the second time, and this is actually a well-known problem. And so another easy way to tackle this is to note that we have a 1 over 1 minus xy, and that's very similar to the form 1 over 1 minus r for the geometric formula. So we can actually expand that out using the geometric formula, so the integral from 0 to 1, 0 to 1. Now, using the summation, n equals 0 to infinity, then this will become xy to the nth power, dx dy. Because all we did is, if you were to use the geometric formula to simplify this, we get 1 over 1 minus xy. So now we can change the order of integration in the summation, so this equals a sum from n equals 0 to infinity of the integral from 0 to 1, 0 to 1 of xy, I'll also make x to the n times y to the n, dx dy. Now this is really easy to integrate one variable at a time. So you have the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 times y to the n, and then evaluated from x equals 0 to 1, and then we have the integral from 0 to 1 dy. So this is equal to the sum from n equals 0 to infinity of the integral, integral from 0 to 1 of plugging 1 into x. We'll be left with a 1. So we have a y to the n over n plus 1. And then plugging in the 0, we'll just leave us with a 0, and that's it. So then dy. So now integrating this back to y, we have this equals the sum from n equals 0 to infinity of, we'll have another n plus 1 in the denominator, and then plugging in the 1 will leave us with 1, and the 0 will go away and go against the 0. So we'll end up with just 1 over n plus 1 quantity squared. Now in order to do this, I'm going to re-index this into the sum from n equals 1 to infinity of 1 over n squared. All I did is just shifted this starting one higher because this is n plus 1. And we know that this is a famous problem, it's the Basel problem, and the famously known result is pi squared over 6. And this is something you should have memorized if you're doing integration competitions because it comes up all the time. So now we're done with this problem. So moving on to question 12. We have a whole bunch of sine of x. And my immediate thought whenever you see trig functions being multiplied together is maybe do product to sum identity. However, that would actually become really ugly in this problem because we'd have to do that multiple times. We have to do sine of x and sine of 2x and sine of 4x and sine of 8x. And simplifying that, would you have to do it again with the second term. And so doing product to sum would actually take a long time. And because this is a times 30-minute test, there's probably going to be an easier, faster way to do it. So then I start looking, well, we have this pattern. We have an x, 2x, 4x, and 8x, and we're integrating from 0 to pi. And so I'm thinking, is there any symmetry on the interval from 0 to pi? So let's start graphing this. So we have from the interval from 0 to pi, 0, let's make this pi over 2, pi. And I'm actually going to keep going all the way to 2 pi just so I can graph it easier. So 2 pi, and then 3 pi over 2. Okay, graphing the sine of x. You'll see why I'm doing this in a second. So graphing the sine of x, we'll have it starting it here. It's going to go like this. Okay, and then graphing sine of 2x, that's going to change the periodicity. So it's actually going to go through 2 complete cycles. So it's actually going to look like this. And it doesn't matter that I'm missing the magnitudes right now. I'm just trying to see if there's any symmetry when you multiply all of these together. So now looking at sine of 4x, well, that's going to complete a full revolution right here. Again right here. Again right here. And again right here. Okay, and then finally, we have the sine of 8x, and now I'm not going to draw it, but basically it goes through a full time, and it's going to hit this point, and it's going to be going basically twice as much as that last one. So now, why did I do this? Now, let's look. So we're on the interval from 0 to pi, so you can basically ignore everything after this point. Okay, so now that we have this graph, I might do an overlay for you so it's easier to see. Let's look at each function at a time. If we were to imagine, let's look at sine x. That's this one right here, the long arch. Now, if we were to imagine, look at this about pi over 2, because that's smack dab in the center. If we were to shift this whole problem over pi over 2 units, and this would be 0, we have this function is actually even about the point pi over 2. So I'm going to write that down. It's even about this point right here. So now let's look at sine of 2x. That's this one right here. That one is odd about the point pi over 2. It goes up first, and then it goes down. So I'm going to write odd. Now sine of 4x, which is this one right here, we know that's also odd about the point because it goes up, down, and then it goes up, down, so it has rotational symmetry of 180 degrees, so it's also odd. Now, I didn't draw the sine of 8x, but you can imagine what it would look like. It's going to go up, down, and it's going to go up, down, right here. And so that's, again, symmetrical about both sides, so it's also going to be odd. So now what happens if you multiply 3 odd functions in an even function? You're going to be left with an odd function. And what happens when you integrate an odd function over an interval about the center? You're going to get 0. So this whole problem is going to be 0. Now, it would take some creativity to see that why it's going to be odd about pi over 2, but if you wanted to prove this rigorously, all you need to do is shift this pi over 2 units to one side. Moving on to question 13, we have another double integral from 0 to infinity, from 0 to 10, of y e to the negative xy, dy dx. Now, in order to do this, I'm actually going to switch the order of integration, because I think it would be easier to integrate the other way first. So, when we do this, we're going to have the integral from 0 to 10, integral from 0 to infinity, y e to the negative xy dy dx. Now, dx dy. Now, when we change this order, in order to integrate this, it's actually very simple because if you were to take the derivative of e to the negative xy, then that would give us e to the negative xy times negative y. So, this becomes integral from 0 to 10 of negative e to the negative xy evaluated from 0 to infinity dy. So, plugging infinity in here will give us a 0. And plugging in 0 here will give us an e to the 0, which is 1, so it's just negative 1. So we have the integral from 0 to 10 of negative 1 dy. And this is obviously really simple. It's just 1 times 10, which equals 10. Moving on to question 14, we have integral from 0 to pi of 1 over 4 minus cosine x dx. Now, when I see this, I immediately think of Weierstrass substitution because we have a trig function, cosine x, in the denominator. And I know that Weierstrass, which I've covered previously, will simplify this into a nice algebraic expression that might be easy to deal with. So in order to do that, it's going to be a u equals tangent of x over 2. Now this makes that 2u over 1 plus u squared equals sine of x. Cosine of x is going to be equal to 1 minus u squared over 1 plus u squared. And then dx is going to be equal to 2 du over 1 plus u squared. So it's actually not too bad to memorize because they're all over 1 plus u squareds. And this sine of x is similar to dx, except it's a du instead of a u. So now, plugging this in, problem 14 is going to become the integral. From changing the bounds, we're going to still get p from 0. And plugging in pi, we have tangent of pi over 2 is infinity. Okay, so now we're going to have 1 over 4 minus cosine of x, which is 1 minus u squared over 1 plus u squared. And then we're going to have the dx is equal to 2 du over 1 plus u squared. Now this is really nice because when we multiply this 1 plus u squared out, it's actually going to cancel over here. So we're going to have the integral from 0 to infinity of 2 du over 4 plus 4 u squared, distributing the 4, minus 1 plus u squared. Now, combining like terms, we have the integral from 0 to infinity of 2 du over 4u squared plus u squared is 5u squared, and then 4 minus 1 is plus 3. Now, this is very similar to the arctangent form, so I'm going to divide by 5 because it makes it easier for me to use the formula. So we have the integral from 0 to infinity of 2/5 du over u squared plus 3/5. Now, using the arctangent form, this is going to be 2/5 times 1 over root 3/5 times arctangent of u over root 3/5, evaluated from 0 to infinity. Now, at infinity, arctangent of infinity is going to be pi over 2. So this will become 2/5 times root 5/3 times pi over 2. Now, arctangent of 0 is 0, so that whole other term will go away. So now simplifying this out, these 2's are going to cancel. And now we're going to have a pi root 5 over 5, and then root 3. So now rationalizing, multiplying root 3 over root 3, this is going to become pi root 15 over 15. Pi root 15 over 15, and that's our final answer for the problem. Okay, moving on to question number 15, we have an integral from 0 to 1 of 1 over 1 plus x to the 6 dx. Now, I'm actually not going to do this problem because it's fairly long and it's a well-known problem. And so on this test, because it was timed, I knew the problem and I knew how to do it, but I actually skipped it. And so in the future, I might do a video on how to do this, but there are also plenty of other sources that explain how to do it. So moving on to question 16 now, we have the integral from 0 to 1 of arcsine of 2x over 1 plus x squared over 1 plus x squared dx. And now something's weird going on here. We see a 2x over 1 plus x squared. Well, if we look back to this Weierstrass substitution we did in 14, we see that form is right here, except it's in terms of u instead of x. So what would happen if you were to try Weierstrass substitution on this, and it's kind of like inverted? So instead of doing this, I'm going to say that x is equal to tangent of u over 2, which is going to make that 2x over 1 plus x squared is equal to sine of u. I'm just inverting this up here. So then we have a 1 minus x squared over 1 plus x squared is equal to cosine of u, and then du is equal to 2 dx over 1 plus x squared. So what happens if we plug that in right here? So we're going to have the integral from, well, plugging in 0 for x, u is still going to be 0. Now plugging in 1, when is tangent equal to 1? Well, tangent is equal to 1 at pi over 4. Doubling it is going to go to pi over 2. Now, on the inside, we're an arcsine of 2x over 1 plus x squared. But 2x over 1 plus x squared is sine, so the signs will actually cancel out, which means with a u on the numerator. And on the denominator, we have a dx over 1 plus x squared. Well, that is very similar to the du, just divided by 2. So we're actually, I'm not going to write anything right there. Sorry, I will do 1. And we're going to have a du over 2. So all this is the integral from 0 to pi over 2 of u du. So, sorry, u over 2. So this becomes 1/4 u squared, evaluated from 0 to pi over 2. So that's going to be pi squared over 4 times 4, which is equals pi squared over 16. Moving on to question number 17, we have the integral from 0 to infinity of log of 1 minus e to the negative x dx. Now, when I see this, I immediately want to use the series expansion for log of 1 minus e to the negative x, because otherwise I don't know an easy way to integrate this. So in order to do that, I'm going to have the integral from 0 to infinity of, now we're going to have the summation from n starting at 1 going to infinity of negative, this part in here, we're going to have an e to the negative x to the n over n dx. So all I did is I plugged this in, e to the negative x into the series expansion for natural log of 1 plus x. So I used the series expansion for this right here, and I plugged in negative e to the negative x. So now all we need to do is flip the order of integration and then integrate. So you have the sum from n equals 1 to infinity of the integral from 0 to infinity of negative e to the negative x to the n, so I'll put that right there, over n dx. So integrating with respect to x, we're going to get, this is going to become the sum from n equals 1 to infinity. Okay, now integrating with respect to x, we're going to get an e to the negative xn over n squared. Now let's check to see if we did that work right. If you take the derivative of this, we're going to have a negative n in front, which should give us what we want. Now from 0 to infinity. Well, at infinity, this term is going to go to 0. And at 0, then we're going to get e to the 0, which is 1. And then that's going to be minus 0 since it's on the bottom. So this is going to be equal to sum from n equals 1 to infinity of negative 1 over n squared. And look at that. What do we have again? We have the basal problem, except it's negative. So by the previously said, that result comes up very often on an integration piece, so it's very helpful to have memorized. So that's equal to negative pi squared over 6. I'm actually going to do a separate video on number 18 in the future, so look out for that. And I will link it in the description once it's out. So moving on to question number 19, we have the integral from 0 to 1 of log of x times log of 1 minus x dx. And I've actually already done a video on this channel on this problem. And it's actually very lucky because when I took this competition, I'd done this YouTube video like a couple days before, so I actually remembered the answer. And the answer to this problem is 2 minus pi squared over 6. So if you want to learn where that comes from, you can go check out that previous video. It'll be linked in the description. So now moving on to number 20, it's actually special because evaluate as a decimal the integral this. And you're scored by how close you are. So there's not going to be a way, because it's approximation, to get an exact answer. So in order to do this problem, you actually know what this graph looks like, or at least that's how I would do it. And it's actually a really interesting graph. So looking at this graph, it's actually going to look very similar to something like this. Except these are going to be slightly curved. So this is going to be a slight curve, this is going to be a slight curve, and this is going to be pi over 2. This is also going to be pi over 2. This is going to be right here pi, and this is going to be 2 pi, and so on, and then it repeats. And so I will show a graph of this on the screen right now. And so all we need to do is we're integrating from 0 to pi of tangent of cosine x. And that's actually approximated very nicely by this triangle right here. So it's a triangle with sides pi over 2 and pi over 2. So the area of that triangle is going to be pi squared over 8. So pi squared is also about 9.86 over 8. So now all we need to do is figure out what that is approximately. So 9.86 divided by 8, it's going to be 1. And then that's going to be 2. So 2 times 8 is 16. 2 is 6. And then we're going to have a 3. And then 24. So it's going to be about 1.23. And so I'm going to say that as my answer because I'm not going to spend any more time on this problem. And it's probably already a pretty close guess. So that's my answer. And I don't remember the exact value, but I will show that on the screen right now so you can see how close it is to the actual answer. So that's it for this test. I really hope you enjoyed. Please like and subscribe if you want to see more like it, and feel free to leave any comments or suggestions down below.